Today we now going to discuss about bounded uniform principle. One important theorem or one important principle which handles functional analysis. We first write this statement of bounded uniform principle. Let X be a Banach space and Y be a norm space. And tau subset of B X Y such that supremum of norm of Tx t belongs to tau less than plus infinity for each x belongs to x. Then norm of tau t belongs to this is bounded. Okay. Then now we're going to prove of this theorem. First, for each n belongs to n, define Cn equal to x belongs to x such that norm of Tx less than equal to n for all t belongs to tau. We proceed with the following steps. Step 1. We have to show that each Cn is closed. Okay. We have to show that each Cn be closed. Now we how we do this is Cn is closed. We're going to further. First, let m belongs to n and let xi be a sequence in Cn. Xi be a sequence in Cn such that xi converts to x for some x belongs to x. Okay. Next is our portion. Then note that norm of Txi less than equal to m for all t belongs to tau and for all x belongs to x. Okay. Then by the continuity of t, norm of Tx less than equal to m for all t belongs to tau. Thus x belongs to Cm. Okay, that means xi be a sequence and this converts to x, and this one also belongs to this sequence. So we find that each Cn is closed. Okay. Okay, that means xi, here we find xi be a sequence in Cm and converts to x belongs to Cm. Hence Cn is closed or Cm is closed. Okay, Cm closed, then each Cm is closed since Cm is arbitrary. Now we're going to step 2. Step 2, what we proved? We have to show that x equal to union of n equal to 1 to infinity Cn. Okay, then how we do it? We know about that Cn subset of x. This implies union of n equal to 1 to infinity Cn subset of x. This one first. Next we show that the converse. Okay, how we show this converse? Let x belongs to x. By assumption there exists mx greater than 0 such that norm of tx less than equal to mx for all t belongs to tau. Okay, one can find an n0 belongs to n. One can find an n0 belongs to n such that norm of tx less than equal to n0 for all t belongs to tau. Okay, then this implies that x belongs to Cn0 subset of union of n equal to 1 to infinity Cn. This implies that x subset of union of n equal to 1 to infinity Cn. This one too. Okay, then we show that x belongs to x and going to this x belongs to this, then this one is done. Okay, now we from 1 and 2 what we get, we erase this portion and we write from 1 and 2 we get x equal to n equal to 1 to infinity Cn. Okay, next we're going to further step 3. Step 3 is more important. Okay, step 3, what we proved in step 3? Step 3, we have to show that norm of t belongs to tau is bounded. note that x be complete. Note that x be complete and Cn be a sequence of closed sets in X, and Cn be a sequence of closed sets in X such that X equal to n equal to 1 to infinity Cn. Then by Bayer category theorem, then by Bayer category theorem, what we get there exists k belongs to n such that interior of ck not equal to phi. Okay, then let x0 belongs to interior of ck, then there exists r greater than 0 such that br x0 subset of ck. Hence tx0 less than equal to k for all t belongs to tau. Okay, let x be a non-zero element of x. Note that x0 plus r by 2 x by norm x difference x0 equal to r by 2, okay, less than r. This implies that x0 plus r by 2 x by norm x belongs to brx0. Okay, then we erase our portion and going to further. T of this implies that T of x0 plus r by 2 x by norm x less than equal to k for all t belongs to tau. Okay, because t belongs to br x0 plus r by 2 x by norm x belongs to brx0. Now norm of t r by 2 x by norm x equal to t x0 plus r by 2 x by norm x difference x0 less than equal to t x0 plus r by 2 x by norm x plus norm of t x0 where x belongs to x. Here x belongs to x and x not equal to 0. Okay, then we erase our portions Okay, and going to further discussion of that, less than equal to this one k, this one k. If this implies that r by 2 norm of tx, here norm of x less than equal to 2k. Okay, this implies norm of tx less than equal to 4k norm x by r. Then supremum of norm of tx by norm of x less than equal to 4k by r. Okay, for all t belongs to tau. Then norm of t also it is our portion. Then what we get? This one equal to norm of t less than equal to 4k by r, where for t belongs to tau. Okay, then this implies that norm of t belongs to tau be bounded. So we prove this uniform boundedness principle. Okay, what we prove? Here x Banach space or complete, then and y norm space, and tau subset of bxy, that means bounded operator from x to y, such that supremum of norm of tau x norm of tx t belongs to tau less than plus infinity, that means bounded. Then norm of t be bounded. We proved it. Okay, so easily we handle this one. And next we going to one important corollary of uniform bounded principle. Okay, we start the statement of this corollary. We write the statement of corollary of uniform boundedness principle. Okay, let x be Banach space. Let x be a Banach space and y be a norm space, and Tn be a sequence in bxy, be a sequence in bxy such that limit n tending to infinity Tnx exists for each x belongs to x, and define tx to y by tx equal to limit n tending to infinity Tnx for all x belongs to x. Let C be a totally bounded set in x, then supremum of x belongs to C, norm of Tnx, difference norm of Tnx difference Tx, norm supremum of x belongs to x tends to 0. Okay, we have to prove it. This one is too easy. X Banach space, y norm space, x Banach space, y norm space, Tn be a sequence in bxy such that limit n tending to infinity tnx exists and txy equal to this, then C be a totally bounded set in X, then supremum of X belongs to C, norm of tnx minus tx equal tends to 0. Okay, we prove this important corollary. Since limit n tending to infinity, since limit n tending to infinity tnx exists, okay, then by uniform boundedness principle, first one t belongs to bxy and second one norm of tn is bounded. There exists a constant m greater than 0. There exists a constant m greater than 0 such that norm of tnx less than equal to norm of tn less than equal to m. Okay, since tm is bounded, we're going to this one by uniform boundedness principle. So there exists, that is, there exists a constant m greater than 0, this one for all n belongs to n. Okay, now we erase our portion, then going to further discussion. Then what we found, since C is totally bounded, since C be totally bounded, there exists x1 x2 dot 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 xm belongs to C such that C is bounded. That is C equal to, that is C subset of P epsilon xi union I equal to 1 to infinity. Oh, 1 to m. Okay. C is totally bounded means some finite number of open ball contain this set. Okay. Then this one, let's see x belongs to C. Then there exists J belongs to 1 to dot 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 m such that x belongs to b epsilon xi. Okay, this implies that is x norm of x difference xi less than epsilon. Okay, now is this lower portion and going to further discussion. Then now norm of tnx difference tx less than equal to tnx minus tnxj plus norm of tnxj difference txj plus norm of tx say difference tx. Okay, then this less than equal to norm of tn plus norm of t xj difference x, or x difference xj plus norm of tn xj difference txj. Okay, then this less than m plus norm t, because norm of tn less than equal to m. Here difference xj norm of this plus this one norm of tnxj difference txj. Okay, then obviously we know about that this one star. Okay, then less than m plus norm of t multiplied by epsilon norm of t and xj difference txj, here pi star. Okay, and we mark it 1. Okay, then what we do, we erase our portion. Then going to further discussion of that. Note that limit n tending to infinity t and xj equal to txj for all j belongs to 1 2 dot 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 n. Then there exists n0 belongs to n such that norm of t and xj difference txj less than epsilon for all j belongs to 1 2 dot 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 n. Okay, now here n for all n greater than n0. Now hence from 1 we get, hence from 1 we get plus epsilon for all n greater than equal to n0 and for all x belongs to c. Thus each x belongs to c, we can find that n0 belongs to n independent from x. Such that norm of t and x difference tx less than m plus norm of t epsilon. The m plus norm of t plus 1 epsilon for all n greater than equal to n0 and for each x belongs to c. This implies that supremum of x belongs to c less than 1 plus m plus norm of t epsilon. This implies that supremum of x belongs to C. Norm of Tnx difference Tx tends to 0. This implies that Tn converges uniformly to T on C. Okay, so today we done bounded uniform principle and an important corollary about this principle. Okay, so today we stop here.